Hello, in this video, you will learn all about inductive reasoning and its many uses in the mathematical world. Also, you'll learn how to find patterns, make educated guesses to prove if it's true or false. So let's talk about briefly what is inductive reasoning. So inductive reasoning consists of three stages. One, looking for patterns. Two, making conjectures. Three, verifying conjectures. So we do a lot of inductive reasoning in everyday life. Conjecture, statement made without conclusive proof. It is an unproven statement based on observation. Example, an educated guess. To verify or prove a conjecture is true, you'll need to prove it is true in all cases. To prove a conjecture is false, you need to prove one single counterexample, just one. Okay? So a counterexample is an example that shows a conjecture is false. So it'll all make sense when we do an example. So example one, describe a pattern in the sequence and predict the next number. So we have our first number is 1. Second number is 4, 3. I mean, the next third number is 7, and then the fourth is 10. So we're dealing with sequences. It's A1, A2, A3, 4. It just means first term, second term, third term, and fourth term, right? So from what from to get the first term to the second term, or one to get from 1 to 4, I believe you had to add 3. And then from 4 to 7, you also had to add 3. And then from 7 to 10, you also had to add 3, right? So the pattern is to add up 3 to the previous number, so the next number would be 13. So the pattern is add 3 to the previous number. So the next number is 13. Okay, so let's move on to the next one. What about example 2? We have 10, 0, -10, and -20. So we'll call this 10 my first term, second term, third term, and then fourth term, right? So to get to the first term to the second, 10 minus, I believe you would have to subtract 10. And then to get from second term to third, you would have to also subtract 10. And then from third term to fourth, you also have to subtract 10. So the pattern is to subtract 10 from the previous number. So the next number should be -30. Pretty simple, right? But they can get more complex. Okay, let's move on. What about 1, 3, 6, 10, and 15? So let's see here. 1, 3, 6, 10, 15. Okay, so this is my first term, second term, third term, fourth term, and fifth term, right? So from first term to second, or from 1 to 3, I believe you had to add 2. Oops. And then to second term to third term, I don't think you had to add 2. What did you have to add? You had to add an extra one more plus 3, right? right? 3 plus 3 is 6. And then from 6 to 10, what did you have to add? You had to add 4. And then from 10 to 15, you had to add 5. So the pattern is to add consecutive numbers. So the next number you would have to add 6. So 15 plus 6 is 21. So the next number should be 21. So the pattern is so the pattern is to add a consecutive number. Next number is 21. Okay, so next one is make a conjecture. So let's look at this word problem. If you cut a string once, 2 pieces are formed. If you cut a string twice, 3 pieces are formed. A string cut 3 times forms 4 pieces. State the generalization. So let's pretend you have a piece of string, right? So let's see. We have a piece of string, and then if you cut it in half, you get 2 pieces. Yes, 1, 2. And if you have the same piece of string, and if you cut it in twice, 2 pieces, how many pieces do you have? 1, 2, 3, right? 1, 2, 3. And then if you have the same piece or same length of string, and you cut it into 3 pieces, 1, 2, 3, how many pieces do you have? So this is 1, 2, 3, 4, 4 pieces. So the conjecture could be cut it once, you get 2 pieces. Cut it twice, you get 3 pieces. Cut it 3 times, you get 4. Cut it 6, you get 7, right? So 3, 4. So basically, if you cut n times, you get n plus 1 pieces. So the conjecture would be cut it n times, you get n plus 1 pieces. Okay. Okay, let's look at example 5. So 10 to the 0 is 1, right? Anything raised to the 0 is 1. 10 to the 1 is 10. 10 to the second is 100. 10 to the third is 1,000. And then 10 to the fourth is 10,000. So what would be the conjecture? So every time you raise a certain value, so the n value equals the number of zeros, right? So yeah, this does not have any zeros because your n value is 0. This only has 1 0 because your n value is 1. This has 2 zeros because your n value is 2, etc. So the conjecture is to the n equals number of zeros. Okay, let's look at example 6. We have 1. We have 1 plus 3 is 4. So wait, 1 equals 1. 1 plus 3 is 4. 1 plus 3 plus 5 is 9. 1 plus 3 plus 5, 7 is 16. And then over here, 1 square is 1. 2 square is 4. 3 square is 9. And then 4 square is 16. So when you're what can we say about the conjecture? You're adding odd numbers to the consecutive numbers, right? So 1 is your consecutive. If you add an odd number, 3, you get 4. And then if you add from here, you add another odd number, that would be 9. And then over here, if you add an additional number, odd number, you get 16. And then what about here? What can we say about this conjecture? The sum of the first odd number, so the sum of the first odd consecutive integers equals n squared. Okay, right, so on the addition part, you're basically adding an odd consecutive number each time, right? Your consecutive, if we started with 1, which is your consecutive number, keep adding odd numbers, this is what you get, 4, 9, 16. And then for the addition is sum, you could say the sum of the first odd number, sum of the first odd consecutive integer equals n squared. Okay, okay, let's move on. So it says complete the table and determine if the conjecture L equals 1/2 P times P minus 1 fits the data. So P stands for point. And then we have to figure out the maximum. So for example, the first one is if you have 1 point, you have 0 lines, right? Max number of lines determined by point. So what does that mean? Here, I'll show you. So if you have 1 point right here, does it form, it doesn't form any line, right? So that's why this is 0. Now let's look at the second one. What about if you have 2 points? Here's 1 point, and then here's another. It looks like if you connect the dots, you can only form one line, right? That's it. You can't form any more. What about 3? If you have 3 points, if you have 3 points, how many lines can you make? So here's line 1, I mean point 1, point 2, and then maybe I could put point 3 here. So if you connect this 2 dots, this forms line 1. And then if you connect these 2 dots, this forms line 2. And then I think if you connect this dot with this dot, you have line 3. So it looks like you can make 3 lines, right? What about 4 points? How many lines can you make? So let's see here. So if I put dot 1 here, and then dot 2 there, and then dot here, and then dot there, connect the dots. So this would be line 1. And then if you connect these dots, this would be line 2. And then if you connect these two dots, this would be line 3. And then if you connect these two dots, this would be line 4, right? And then is there any more lines you can make? Yeah, right? If you connect this line, that would be line 5. If you connect this line, that would be line 6. So it looks like you can make 6 lines. Okay, what about 5 dots? So that's a little bit trickier. So let's just stick with this image because this already has 4 dots, and then the last dot would be let's put a dot here. So now we have 6. Uh, so I think if you connect this dot here, that would be line 7. If you connect this dot here, that would be line 8. And then if I here, let me use another color. I see one more dot. If you connect this dot with this dot, that would be line 9. And then if you connect this dot, let's say this dot right here, this dot, that would be line 10. So it looks like you could form 10 lines. Okay, now let's see if because we completed the table, now let's see if the conjecture is true. So they're saying that L equals 1/2 P times P minus 1. So L represents a line. So let's just plug in, what should we plug in? Let's plug in 4. So we have 4 points. Will we get 6? So it would be 1/2, and then this is 4, and then 4 minus 1. That will give you 1/2, 4, and then 4 minus 1 is 3. So 4 times 3 is 12, divided by 2, that's 6. And yeah, you get 6 lines, so that's true. What about 5? It would be L equals 1/2, and then 5 times 5 minus 1 is 4. 5 times 4 is 20. 5 times 4 is 20, divided by 2 is 10. So yeah, that works. What about 3? It would be 1/2 times 3. 3 minus 1 is 2. 3 times 2 is 6. 3 times 2 is 6, divided by 2. That would be 3. Yes. What about 2? 2 minus 1 is that. So 2 minus 1 is 1. Times by 2, that's 2 over 2, which is 1. Yeah, that works. And then what about 0? Yes, that would be 0 and 2. That's definitely true. 0, 0. So yes, you can say yes, it fits the data. Okay, next one says show the conjecture is false by finding a counterexample. Show the conjecture is false by finding a counterexample. So are all prime numbers odd? So what are all prime numbers? One, are all prime numbers odd? So what are some examples of odd numbers? One, or all prime numbers are odd. So I mean, what are examples of prime numbers? So one, and prime number is can only be times by one itself. So one is prime, three is prime, five is prime, seven is prime. What else? 11 is prime, 13 is prime. Uh-oh. Um, oh, yeah, that's odd. What about two? Isn't two prime? Because two can only be multiplied by one in itself, right? So that makes it prime. But it's not odd, it's even, right? So the number two is prime, but not odd, but even. Okay, what about number nine? All fruits have seeds on the inside. So what are examples of fruits? And do they all have seeds on the inside? So apple is a fruit that has seeds inside. What about watermelons? Yes, that has seeds inside. Peaches, yes. I've never seen a peach with seeds outside. Oh, what about the fruit strawberry, right? That has those little those little dots outside the strawberries, those are seeds. So so you could say yeah, strawberries have seeds outside. I mean, yeah, strawberries have fruits. I mean, strawberries have seeds outside. Okay, let's move on. The sum of two numbers is always greater than the larger number. Okay, so it doesn't say like odd or even numbers. It just says the sum of two numbers is always greater than the larger number. So let's see. The sum of two numbers may be like 2 plus 3. That's 5. Greater than the sum of two numbers. So that checks out. What about 3 and 7? That's 10. So they say two numbers. It didn't mean positive. Both numbers have to be positive. One could be a negative. So an example would be like 5 plus negative 3. That gives you 2. So this 2 is less than 5. So this is where it's false. So this is this right here, 5 plus negative 3. That would be the conjecture. That shows that the conjecture is false by finding a counterexample. So yeah, 2 is less than 5. And this shows the sum. is not always greater than the largest number. Okay, so on the next one, more, just two more. Okay, the square root of number is always less than n. So is that always true? So square root of n, the square root of a number n, the square root of a number n is always less than n. So square root of n, mm, let's try square root of 4. Square root of 4 is 2. Yeah, that's true. Square root of 9 is 3. Yes. Square root of 100. Yes. What about square root of, I don't know, decimals? So like maybe square root of 0.25. That is 0.5, right? So this is a false statement. This proves that this proves that this conjecture is counterexample. So you could say, yeah, 0.5 is greater than 0.25. Okay, last one. If the product of two numbers is even, then the two numbers must be even. So if the product of two numbers is even, then the two numbers must always be even. So they don't know, let's call our two numbers x and y, right? And it's supposed to spit out an even number. Let's see if that's true. So how about 2 times 4? These two numbers are even, and it spits out 8, which is even. What about so wait, no, the two numbers doesn't have to be even. They could be a mixture of even or odd. It's just that whatever it spits out has to be even. So what about 2 times 3, right? These two's an even, three's an odd. Does this spit out an even number? No. Yes. So yeah, even times odd equals even. So let me the product of two numbers is even, then the two numbers must be even. So yeah, this is false. If the product of two numbers is even, so 2 times 3, 2 is an even, 3 is an odd. I had to think about it. 2 is even, 3 is odd. This spits out 6, which is even. So yeah, this is a counterexample. So even times an odd, you can say even times odd is even. Okay, that was the last example for this lecture, so I'm going to stop here.